Hello everyone, and welcome. I'm excited to introduce today's presentation on the smart HVAC system with solar integration. We'll explore how this innovative approach provides efficient cooling for buildings using a solar-assisted chilled water system. Throughout the session, we'll look at how photovoltaic panels help power the chiller, pumps, and air handling units, reducing electrical demand and boosting sustainability, especially in hot, dry climates. Let's get started. Let's take a closer look at the quick cooling load for the dorm in the hot, dry climate of KSA. The peak cooling load reaches about 205 TR, which is roughly 720 kilowatts. To put that into perspective, that's the maximum cooling capacity needed during the hottest times. The load corresponds to a density of around 120 watts per square meter. Over the course of a year, the total cooling demand sums up to approximately 451,000 TR hours. This figure highlights the significant energy requirements to maintain comfortable conditions in such a hot environment. Understanding these peak and annual loads is crucial for designing efficient cooling systems that can handle the demand without excess energy use. It also underscores the importance of optimizing cooling strategies to improve energy efficiency in these challenging climates. Let's take a closer look at the system options and their impact on annual energy consumption. The VRF system, in particular, offers a significant advantage here. It saves approximately 20% of energy compared to a traditional air-cooled chiller. To put that into perspective, that's about 126 megawatt-hours less energy used per year. This difference not only means lower operating costs, but also a more sustainable and environmentally friendly approach. It's a clear example of how choosing the right system can make a big difference in overall efficiency and long-term savings, which ties back to our overall goal of optimizing performance and reducing energy footprints. Let's take a closer look at the solar PV system. On an average day, this system can generate power for about 9 hours. That's a significant amount of sunlight contributing to our energy needs. Specifically, a 300 kilowatt peak PV system can produce around 657 megawatt-hours annually. To put that into perspective, that's enough energy to power a substantial portion of our facility's requirements. Interestingly, about 70% of this generated energy is used directly for our HVAC load. This highlights how effective solar can be in meeting major energy demands on site, reducing reliance on external power sources. By integrating this solar setup, we're making a strong move toward sustainability and energy efficiency, aligning with our broader goals of reducing carbon footprint and operating costs. Now, let's take a look at the financial impact of these cooling solutions. The bill impact is approximately 0.18 SAR per kWh. By implementing VRF systems combined with photovoltaic, or PV, technology, we can save around 82,800 SAR annually compared to traditional chiller systems. This represents a significant reduction in operating costs, which not only benefits the bottom line, but also aligns with our overall goal of more sustainable and cost-efficient building management. This slide highlights how choosing the right technology can make a real difference financially while supporting our commitment to energy efficiency. All right, let's talk about what to install and how to make the best decision for your system. When choosing between VRF and chillers, it really comes down to the specific needs of your project. VRF systems are excellent for small zones and situations where you want to maximize part load efficiency. They allow for precise control in different areas, which can lead to significant energy savings and improved comfort. On the other hand, chillers are typically better suited for central expansion, especially when you're dealing with larger spaces or a more extensive system. They can handle higher cooling loads efficiently when integrated into a centralized setup. So the key is to assess your project's size, zoning, and load patterns. If you have smaller, varied zones, VRF might be your best option. But if you're planning a larger, centralized cooling solution, a chiller system could be more effective. By making an informed decision here, you're aligning your equipment choice with your overall energy efficiency goals and operational needs. Let's take a closer look at the VRF and chilled water concept. On this slide, you can see that we're utilizing rooftop VRF systems, which are highly efficient for flexible cooling and heating. These systems work well in modern buildings by providing targeted comfort while reducing energy consumption. In addition, we're incorporating DOAS, or dedicated outdoor air systems, to bring in fresh air, ensuring good indoor air quality. This is especially important in today's focus on healthy and comfortable indoor environments. We also have two 120TR chillers as an alternative, offering redundancy and increased capacity when needed. This setup ensures reliable cooling performance across the building. Finally, the integration of a 300 kW photovoltaic system adds a renewable energy source, helping to offset the building's power consumption and improve overall sustainability. Altogether, this concept demonstrates a comprehensive approach to energy-efficient, sustainable building climate control, aligning perfectly with our overall goal of creating smarter, greener buildings. Let's talk about how we can adjust for different buildings. When we look at a scale of 205 TR with watts per square meter, an increase of about 10 Wm2 roughly translates to an additional 15 TR. This means that even small changes in the building's heat load can have a significant impact on our overall calculations. It's important to remember that whenever we make these adjustments, we need to recompute the energy consumption in kilowatt hours and the specific absorption rate, or SAR, accordingly. This ensures our analysis remains accurate and tailored to each building's unique characteristics. By understanding these adjustments, we can better compare different buildings and optimize their energy performance. This ties back into our overall goal of creating efficient, sustainable designs that are customized to specific environments.